3U, we are on quadratics day 8, our last lesson for the quadratic unit, and by far my favorite. We are looking at linear and quadratic points of intersection. So Joe has decided to go skydiving, and after he jumps out of the plane, he will free fall for a while. This is modeled by minus 4.9 t squared plus 5500. So we have a parabola that has a pull of gravity downwards. And we have an initial height when he's on the plane. So we know what the path would look like if he just jumped. He would start at 5,500 feet, and he would start picking up speed and picking up speed and picking up speed by the force of gravity, and he would very likely die. So we have Joe. This is not good. I don't know how to draw angels very well, but anyway, there's Joe. This is not a good scenario if he were just to free fall. So he decides to pull his parachute knob. That's a different equation altogether. Minus 5t plus 4,500 would be a straight line type of a deal, which is a nice gentle fall, and he can walk away happy and safe. But he's a bit of a daredevil, and he wants to kind of balance those and find the point that he has to pull that parachute knob in case, so that he doesn't die. So we want to put these two together, find the point of intersection, which will allow him to have fun and still live. So we want to find this magic place right here that he can pull his parachute knob and live. So if we were to model Joe's path, he would be accelerating towards the Earth, and then he would open his parachute and gently come towards the Earth. I mean, too fast for my liking, but nevertheless, life-saving principle. So we want to know where that is in terms of time. In order to find a point of intersection, when we did lines, we set one thing equal to the other. So if we had his parabola, I have to go back and find that equation, minus 4.9 t squared plus 5,500. And we set it equal to that line of descent, we can find a point of intersection. This is substitution, really. Just looking a little more difficult. But we know if we're asked to find a solution for t, and we have a quadratic equation, we know we can use the quadratic formula, or complete the square, or factor. So let's tidy that up and solve for t. All right, I'm going to get everything on the right side by adding 4.9 t squared minus 5t. I'm going to subtract 5,500 from both sides, and I have a quadratic equation equal 0. I'm a little on the lazy side today, so I think I'm going to use the quadratic formula rather than try to complete the square with that thing. I'm going to possibly get two answers for t. Why? Because the formula doesn't know that this domain only makes sense when t is greater than or equal to 0. We don't actually know what t has to be less than. We don't know what that number is. But the equation would project that there would be another solution where that parabola would meet the line back here. But that wouldn't make sense in our question. Let's see what we get. Negative b. Let's write the formula out. Negative b plus or minus the square root of b squared minus 4ac over 2a. Negative b would be a positive 5 plus or minus b squared is 25 minus 4 times 4.9 times negative 1,000. All over 2 times a is 2 times 4.9 is 9.8. I'm just going to get this in the way. There we are. I'm going to use my calculator to find 25, and a negative times a negative is a positive. 4 times 4.9 times 1,000 is 19.6 times 1,000. Should be that. I'm going to check with a calculator though. Yay, good for me. Over 9.8. My t-values are approximately, and I'm doing 5 plus the square root of 19,625 divided by 9.8 as one of my possible t-values, which is 14.8. The other possible t-value is 5 subtract square root of 19,625. 5 subtract divided by 9.8. My second t-intercept is possibly minus 13.8. We can disregard that. Negative time doesn't make any sense in our problem. So we are suggesting that Joe should open his parachute before 14.8 seconds has elapsed. Let's do a few that are a little less life and death. We're going to find the point of intersection by graphing, and that's how we started with linear systems in grade 10 as well. First of all, we're going to do f at x, which is your basic parent function for quadratics. So I know my step pattern. I'll draw a rough graph of that. Y equals x squared parabola. There we are, f at x. G at x is the line with a vertical transformation up 6. My y-intercept is there. My parent function with your basic slope of 1 is that guy, sort of. So it appears that I have 2 points of intersection by eyeball. Not the best method, but it appears we have 2 points of intersection. One of them appears to be 3, comma, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 9. And the other one appears to be minus 2, 4. These points of intersection might be a little trickier to graph and see. We're going to do it by setting one equal to the other. Minus x squared plus 6x minus 5 equals minus 4x plus 19. To solve for x, I want to isolate everything on one side equals 0. And we know then we would use the quadratic formula, factor, or complete the square. I am going to put everything on the right side equals 0. Totally up to you which side you go for. I'm going to add x squared to both sides. I am going to subtract 6x from both sides. And lastly, I'm going to add 5 to both sides. I could use quadratic formula, but factoring is far faster if it's possible. So I'm going to take a quick second and see if I can factor since it's a simple trinomial. Simple trinomial would be factored as x and x. Two numbers that multiply to a positive and add to a negative would both be the same sign and would both be negative. Multiplying to 24 and adding to 10 would be a 6 and a 4. So since this was so nicely factorable, I have two places where there are points of intersection, where x is 6 and where x is 4. but those aren't points. Those are just places where. So for points of intersection, I know that one of them has an x value of 6. The other has an x value of 4. And to get the corresponding y values, I would need to substitute x equals 6 into the equation of the line or the parabola, and I'm going to substitute x equals 4 into the line or the parabola. Let's do substitute x equals 6 into g of x. G of x is minus 4x plus 19. Minus 4x plus 19. Minus 4 times 6 plus 19 was minus 24 plus 19 is minus 5. I have a point of intersection. For my second point of intersection, I need to find either g or f at 4. I'm choosing g because it's just simpler to work with a linear equation than a quadratic. Minus 4x plus 19. Solve for that. Minus 16 plus 19 is 3. So my y value for my other point is 3. I have 2 points of intersection. For this equation, we're actually not asked to find the points of intersection. We're asked to find the number of points of intersection. So if I were going to find the actual points of intersection, I would set f at x equal to g of x. So I'm going to proceed with that. 4x squared plus x minus 3 equals 5x minus 4. And if I were going to find those points of intersection, I would set it equal to 0 and everything on one side. I'm going to go for the left this time. I'm going to subtract 5x from both sides. Oops. I'm going to do all sorts of magic. I'm going to subtract 5x from both sides. That means I will have minus 4x. There we are. I'm going to add 4 to both sides. There. Now that I have it in a quadratic form equal to 0, I know that I could find my points of intersection by using the quadratic formula. But the quadratic formula can actually tell me how many solutions for x I would get. And that tells me how many points of intersection for f at x and g at x I would have. So from here, once I have set them equal to each other, I can use the discriminant b squared minus 4ac to tell me how many solutions I would have to this problem of points of intersection. B squared minus 4ac, when I have set it up as ax squared bx plus c, my b squared minus 4ac is equal to minus 4 squared minus 4 times 1. So I've substituted the values into b squared minus 4ac. I will get 16 take away 16, which is exactly 0. If my discriminant is 0, that tells me I have one solution. And so, for f at x equal to g at x, there is one solution. That means there is one point of intersection for f at x and g at x. Looking at points of intersection, please try page 198, 1b, 2b, 4, 6 to 10, 12, and 14, and there are no course notes pages for that. Don't forget you do have a graphic organizer that's due as well.